Hello, hi. So last time we finished the first chapter, and one of the lessons of the first chapter was that we are studying linear combinations. When we're talking about solving linear systems, we're really talking about taking linear combinations of the rows. We're studying linear combinations. So in this chapter, we want to expand what linear combinations are about, so that today's check-in is that first step in that direction. Here I have a linear combination of three vectors. Not a linear combination of numbers like we saw in a lot of the previous chapter, but a linear combination of three vectors. We've already seen some of this when we wrote the solution sets of linear systems and when we wrote the equations of planes, but nonetheless I'm making it explicit here. This is a linear combination of three vectors and we're asked to solve it. So we're thinking about what can happen when you try to do equations involving these objects. Okay, so let's write it down. So I want to take the linear combination of those three vectors, and so I have, just to start in here, I have 1, 2, 0 times x, 1, 1 minus 1 times y, and 0, 3, 0 times z equals 0, 0, 0. I like the 0, 0, 0, the homogeneous case, for reasons that we'll see later on today. And I want to figure out what x, what y, what z makes this true. So this is just like when you had numbers, except now it's letters. And of course, we've seen this already, but I'm trying to bring out a fact that we're taking linear combinations of things other than numbers. Okay, so of course, a person thinks to look at the first line and get, let's see, x plus y equals 0. The second line gives you 2x plus y plus 3z equals 0. And the third line gives you minus y equals 0. And these zeros over here means that you cannot have a contradictory equation. So you've either got one solution or infinitely many solutions. I don't know, I'm not going to actually solve it because watching me do arithmetic is not very interesting. So the point though is that off we go. Gauss's method gets us an answer. That's all we need to know, is that we can solve that, and then off we go. Okay, next up though, I want to underline the same thing here, is that we can take linear combinations of things other than numbers. So here I am taking a linear combination of matrices and asking basically the same question, is can you give me a solution, an x, a y, and a z, that makes this particular linear combination equation true? And of course, for number 2, of course, it's exactly the same idea. The point was to illustrate that I can take linear combinations of things other than numbers in some reasonable way. All right, so just to illustrate here, I get the system 2x plus y equals 0. That's from the upper left. From the upper right, I get x minus y equals 0. And the lower left gives me 1/2 y minus z equals 0. And then the lower right gives minus 2x plus z equals 0. And again, I don't really care about what the answer is. The point is that I can do Gauss's method. Off we go. We get an answer. So I can make sense of trying to figure out linear combinations of things other than numbers. We started out with chapter 1 by thinking about linear combinations of numbers, 3x plus 2y minus z equals 7 kinds of systems. Here we're thinking about things other than numbers, and that's the thing that we're introducing in this chapter. Okay, so let me bring up what it is that we want to talk about today. We want to talk about taking linear combinations, what it means to study linear combinations, taking linear combinations of things that could be numbers, but could be other things, like linear combinations of vectors. We already saw that in chapter 1. Linear combinations of matrices, linear combinations of whatever you happen to want to be taking linear combinations of. Okay, so that when you say you're taking linear combinations of things, you're going to formally describe that. When you say, I want to be in a place where I can take linear combinations, you formally describe that by saying, look, I'm studying a vector space. And you have to say what particular vector space you're studying. So a vector space is a category of problems, but nonetheless, we're going to study that category. So first, of course, I have to define it. I'm going to give a number of examples because it is the central object of study of the course, but I only can get one example onto the video today, so that the follow-up video will contain a number of other examples, so I'm not just going to leave you with one. Okay, so here's the definition. In fact, it's not even the whole definition. In fact, there's another 5 conditions, but I broke it into two different slides just to try to illustrate what's happening. So a vector space V, there are many different vector spaces. There is, for example, the vector space of all 3 tall vectors. We just saw that in the check-in. There's the vector space of 2x2 matrices. We also saw that in the check-in. So there's going to be piles and piles of vector spaces. We'll see dozens of vector spaces over the course of the semester. All those vector spaces satisfy a number of conditions, and we're writing down the conditions that they all satisfy. In every one of those cases, vectors or matrices, there's a plus operation and there's a times operation. The plus operation, for example, the plus operation between vectors, and the times operation is, for example, the 3 times a vector or 5 times a vector. That is to say, this is scalar multiplication, multiplication of a vector times a scalar. This is called a vector space. Sometimes it contains vectors, but sometimes it contains other things. It can contain, for example, 2x2 matrices. Vector space is just a word. When you look at the conditions, and I already mentioned there's 10 conditions, when you look at the conditions, they break into 2 different kinds of conditions. There are conditions here like 1 and like 6, and there's also conditions, the rest, 2, 3, 4, and 5, and 7, 8, 9, and 10. I'll look at the 2, 3, 4, and 5 first. 2, 3, 4, and 5 describe something about linear combinations. So for example, we will consider that if you had some kind of plus operation that was not commutative, then we won't think of that as a linear combination. That linear combination, really the plus operation has to be commutative. If you add 2 vectors, that's commutative. If you add 2 matrices, that's commutative. So we're thinking of the plus operation has to be commutative, or else we won't consider it a legal case. Likewise for associative. There has to be a 0 object. There's a 0 3 tall vector, there's a 0 2x2 matrix, etc. There has to be a 0 object. And you have to be able to cancel. So if you have the vector 1, 2, 3, and you add it to the canceling vector, the -1, -2, -3, you get the 0 vector. And so we'll consider that if you don't satisfy those properties, you're not really the kind of plus that we're thinking about. Condition 1, the condition of closure, is the one that we'll talk about the most. It is the one that turns out will be adds the real flavor to the subject. It's the one that's most interesting to us. And you see the same thing for condition 6. So condition 1 and condition 6 both say that the space has to be closed under those operations. That is to say, if you add 2 vectors, you have to, if you add 2 members of capital V, you have to get a member of capital V. If you, in condition 6, if you take a member of capital V and you multiply it by a scalar 3 times or 4 times or 5 times or 0 times, you have to get a member of capital V. And then you see conditions 7, 8, 9, and 10 are similarly conditions that a person thinks, if you didn't have them, you wouldn't really think of this as a scalar multiplication. That applying the word scalar multiplication would be a very peculiar thing to do if you didn't have conditions 7, 8, 9, and 10. Just as a for example, if you had something you called scalar multiplication, and multiplication by 1 didn't give you back the vector you started with, if you took 1 times v, you didn't get v, you'd say, I'm not thinking about that case. That's a case that is not on my plate at the moment. Okay, so for example, a scalar multiplication distributes over addition. We'll expect that in the collections that we look at, for example, the collection of 3 tall vectors or the collection of 2x2 matrices, in the collections that we look at, you can always distribute scalar multiplication over vector addition. And again, the word vector doesn't necessarily mean 3 tall vectors or 4 tall vectors or 5 tall vectors. It might mean 2x2 matrices. I'm sorry, just a historical word that we're stuck with. Okay, so there are many familiar vector spaces. We're going to talk about the familiar cases soon enough. I can only fit so much on one video, but I'm going to start off by looking at a less familiar case, because sometimes the best way to understand something is to look at not the first case that a person runs across. So here's the very first example I want to do. I want to look at this line that passes through the origin. So this is a line in the plane. Here's the plane. It's a line in the plane, and it's all the multiples of the vector 1, 2. You see 1, 2 is in blue here, so this is the line with slope 2 that passes through the origin in the plane. That's a collection of vectors. It contains, for example, 1/2, 1. It also contains 2, 4. It contains -1, -2. It contains 0, 0. So this set, capital V, is infinitely many vectors. I'm going to contend that this set satisfies all 10 of these rules. Of course, I'm going to check them. I'm going to check them at some length. Some of the rules are very obvious. Almost all of them are very obvious. The two that will usually concern us are Rule 1 and Rule 6, the rules about closure, that if you add two members of this space, you get a member of this space. And if you multiply a member of this space times a scalar, you get a member of the space. Okay, so here we go. I'm gonna walk through the conditions, but before I do, it's very important not to lose the forest for the trees. The point of vector spaces is that vector spaces are a place where linear combinations happen. So if I'm looking at the vectors that are that have the property that the second component is twice the first, second component is twice the first, second component is twice the first. If I'm looking at vectors with that property, I should be able to take linear combinations of them. What do you mean by should be able to? Well, there I am with a linear combination of them, and I get a result, 5, 10, with the same property. The point of vector spaces is that you can take linear combinations and not be afraid that when you do the arithmetic, you'll find yourself with something that is not in the space. Instead, anytime you take a linear combination of members of the space, you get a member to the space. That's the point. So when I say linear combinations can happen in this space, exactly what I mean is that if you take linear combinations, you stay in the space. Okay, so I have to tell you what the operations are, and we know the operations because we studied them already. We had a review, but I suspect that a person, most of the time when a person came to this class, they already knew that if you add a pair of two tall vectors, you get this way of getting a two tall vector. You add them component-wise. And same thing, scalar multiplication, you multiply by 3 times 5 or by -1. You just multiply the components by 3 or 5 or -1. The first condition, closure, is that the sum of two members of V is also a member of V. And the only tricky part to understand here is what is it you're required to check. You have to check that if you take two members of the space, and remember, member of the space means second component is twice the first. So if you take two members of the space, two vectors with the property that the second component is twice the first, the second component is twice the first, I wrote it there, then you'll get a vector with the second component twice the first. So of course, here's the two vectors, here's me adding them. I have to check that y1 plus y2 is twice x1 plus x2. Well, of course it is, because if you add these two together, then you get twice x1 plus x2 and you're done. So it's not hard to do. The hard part here is to understand what you're asked to do. What you're asked to do is to check that if you have two vectors from the space and you add them according to the rules of addition, the regular sort of physics 1 rules of vector addition here, you get a member of the space. Get a member of the space means second component is twice the first. So we checked it, so that's good. Condition 2, commutativity of addition. You have to check that if you add two vectors either as v1 plus v2 or as v2 plus v1, you'll get the same thing. And really, the problem with these, with some of these conditions, 2, 3, 4, 5, is that it's not that they're too hard, it's that they're too easy, and a person has trouble figuring out what exactly is it that happened. So I'm going to compare v1 plus v2 to v2 plus v1 and note that they're the same. And of course they're the same. x1 plus x2 is a real number. x2 plus x1 is a real number. And you add real numbers in the opposite order, doesn't matter. y1 plus y2, y2 plus y1 are the same real number. The order doesn't matter. So commutativity of addition here we say inherited from commutativity of real number addition. But in any event, it's not that hard. The hard part is figuring out what it is that you're asked to do. So some conditions have nothing to do with the fact that y1 equals 2x1 and y2 equals 2x2, and this is an example of such a condition. I mentioned that conditions 1 and 6 will be the ones that mostly concern us. That's because they're the ones that it will involve that. And again, just going slowly through conditions 1 through 10, trying to answer a question so that a person can say, well, when I got to the homework, I knew what I was asked to do. Associativity of addition, I have to check that if you do V1 plus V2 and later on add V3, you'll get the same as if you do V2 plus V3 and later on add V1. And I'm not saying it's hard, I'm saying the hard part is to understand what you're asked to do. So here, V1 plus V2 later on add V3 gives you this. And V2 plus V3 later on add V1 gives you this. And of course they're the same because real number addition is associative. So again, didn't need the second component is twice the first, didn't need it. Condition 4 just says that there's a vector that when you add it to other vectors doesn't do anything. And again, a person can say, well, I wasn't sure what I was being asked to do here. So you're being asked to exhibit that vector. Name a vector with the property that when you add it to other two tall vectors, it doesn't do anything. And I go, nobody has trouble naming the vector. You just have to name it. Of course, I verified that when you take a vector and add 0, it doesn't change the vector. But the hard part is not doing it. The hard part is understanding what you're asked to do. 5, same thing, it says existence of an additive inverse. So you're asked to name. If you're given a vector that's a member of the space where y is twice x, what would you add to this to make it equal 0, 0? And I know everybody knows. The answer is you add minus x and minus y, and the y equals minus 2x here. The only thing you have to worry about is, does minus x and minus y live in this space? If xy is in this space, is minus x and minus y, is that vector in this space? And the answer, of course, is yes, because if y is twice x, then minus y is twice minus x. And I wrote all that stuff down. But again, the question is usually figuring out what it is you're asked to do. The condition asks you to show there is an additive inverse. The easiest way to show something exists usually is to just produce it. So I was given an xy, subject to the condition, given an xy where I got the vector v in capital V, and asked to produce a w that cancels v, and then verify that w is also in capital V. I verify that w is also in capital V by verifying that minus y is twice minus x. Okay. Next up, I'm on to the conditions that really talk about scalar multiplication. I just broke it in two just to try to break the job up into smaller parts. So condition 6 is about closure under scalar multiplication. So I have to start with a vector from the space, v in capital V, and I have to multiply it by a scalar. And I got to show that no matter what scalar I multiply it by, the result, written right here, the result is still in capital V. In capital V means that its second component is twice its first. So if I start with a vector where the second component is twice the first, and I multiply it by, say, 108, do I get a vector whose second component is twice its first? Well, of course you do. Because if y is twice x, then ry will be twice rx. That's not hard. None of these are hard. The hard part is understanding what a person is asked to do, because very, very typically, almost 100% of the time, this is the first time a person has seen this kind of thing where you're required to check the conditions on a structure, and so you're like, oh, I'm not 100% sure what I'm doing. Never done this before, so that's why I'm walking through these one at a time. None of them is hard. Every one of them leaves a person thinking, am I sure I was supposed to do that? So that was 6. That's the other closure condition besides 1. The closure conditions are the ones that we'll usually be paying attention to. 7. So to check that real number addition real number addition distributes over scalar multiplication. So we just check here that there we go, that r plus s multiplied by v gives you if you take v in the vector space capital V, do you get a result that's in the same vector space? So if y is twice x, will ry plus sy be twice rx plus sx? If v is in the vector space capital V, will rv plus sv be? And the answer, of course, is yes. That's easy to see, but it's a person has to know what to check. The next one, maybe you're getting kind of the swing of this. You'll have r times v1 plus v2, and you're comparing it to rv1 plus rv2. And do you get that? And again here, when you do, as with the previous question, when you do r times v1 plus v2, you get this. When you do rv1 plus rv2, you get this, and they're equal because r times v1, excuse me, r times x1 plus x2 is equal to r times x1 plus r times x2, just because they're real numbers. R times y1 plus y2 does equal ry1 plus ry2, just because they're real numbers. So that's 8. 9. We have to do here two real numbers that are multiplied together, two scalars here. So it might be 7 times 5 multiplied times the vector v. You get the same result as if you took 7 times 5 times v. And you just check here, rs, the definition of rs scalar multiplied times v is rs by the x and rs by the y. The definition of r by sv is r by sx and r by sy. And of course these are all real numbers, so they all come out equal. That's all right. That's all correct. Okay. And then the last one, condition 10. Condition 10, you just have to check that multiplying 1 times a vector. If you work your way through the definition of multiplying 1 times a vector, does it change the vector? And of course it doesn't change the vector. Of course it does. Okay, so what we've done is we've worked through conditions 1 through 10. Worked through conditions 1 to 10. Many of them were routine. Many of them, there was really very little to do in some sense. We had to recognize, though, the concept of what we were doing. So we had to recognize, for example, what does the question ask us to do? When we say there is a 0 vector, what am I asked to do? And the answer is, it says there exists. So we produced it. We produced the thing which, when you do the defined operation, doesn't change the vector. For condition 2, we had to write down the left-hand side, v plus w, and the right-hand side, w plus v, and check that the two of them are the same vector. So for many of these cases here, for example 9, 8, for many of these cases it's extremely easy to check. It's a question of knowing what to check. So the difficulty is figuring out where it is you're asked to proceed. The ones that are more interesting is a mathematical word that means sort of hard, or maybe the heart of the question lies here, is conditions 1 and condition 6. In condition 1 and condition 6, we had to check that if you add two vectors, add two members of the space, you get a member of the space. And if you multiply a member of the space times a vector, times a scalar, you get a member of the space. So if you take two members of the space and add them, you get a member of the space. The space is closed under addition. Down here, if you take a member of the space and multiply it by a scalar, 10, 12, 108, minus 6, 0, you get a member of the space. Those are the ones that will turn out to be the crux of the matter. Most of these other questions, it's not that they're stupid, it's that they're routine, or they tend to come out to always be so. Okay, very good. Okay, so that was a long one, but I'm not going to leave you with just one. I'm going to go through and do on the next video, a bunch of examples so that a person, when you come to the homework, can feel like, okay, I have some idea what it is I'm asked to do. It turns out that questions 1 and question 6 here, conditions 1 and condition 6, are the heart of the matter, and that's what we'll focus on in the next slide. So let's see here. Next part will be the definition of vector spaces, part 2, and we'll see you then.